So we've reached the end of this 3-module course on advanced fluid mechanics. And it'd be nice to try and make a summary of the whole class. That's very difficult to do in one slide, but Bhavand is going to give a couple of last examples and a last recitation. And instead, what I'm going to do is just give you a 1-page overview that kind of summarizes the key equations of fluid mechanics that we've learnt about in this class. And of course, they're all really centered around this main equation, which is the Navier-Stokes equation that we're going to think about for isothermal flow of an incompressible Newtonian fluid. And really, all of the parts of the class are connected to this equation in various forms. For example, we started right back at the beginning by turning off all flow and thinking about just the interaction of body forces, and that led to this equation that we called the central equation of hydrostatics, that gradients of pressure can balance accelerations. And so if we have, for example, a glass of water at rest, then we know that there is a pressure gradient inside the material and a higher pressure at the bottom. We also thought about rigid body rotations as well as circular motions or circular rotations, and found the pressure fields associated with that. Towards the very end of the class, we've also thought about what happens in a system where we have an interface or a meniscus. And then we've seen the idea of the Young-Laplace equation, where we might have principle of radii of curvature, R1 and R2, and there can be a pressure difference across the interface associated with that curvature. And even in static situations, the nonlinearity of these expressions that we found for R1 and R2 mean that it can be non-trivial to find even static solutions to the equations of motion. But this idea of surface tension is effectively a boundary condition that we can apply when we solve the Navier-Stokes equations. So we then really began in Module 1 by thinking about an inviscid flow where we turned off the viscous contribution to the stresses, and we just thought about what we called the Euler Equation. The idea that the material derivative gives rise to an acceleration that is balanced by pressure gradients as well as body forces on the system. And we thought about 3 different forms of that equation that we could get by integration. One of them was by integrating along a streamline, and that gave rise to Bernoulli's equation for a steady flow along a streamline. And then we also thought about applying this equation across a streamline, where a streamline is nice because the streamline only has one component of velocity. The velocity is always tangent to the streamline. So that means that this turns into a differential equation for the pressure variation across a streamline. And those pressure variations across a streamline can balance accelerations. And so, for example, we found that when we looked at the eye of a hurricane or a tornado, that because of the circular motion, there's a pressure gradient across the streamlines and a low pressure at the middle, and a large pressure, which is atmospheric pressure, at the middle. So when we think about the eye of a storm, we have a low pressure that depends on the velocity field v squared and the radius of curvature r. We also even thought briefly a little bit about unsteady forms of this equation, where we recognize that if we have an unsteady form, then we're going to be able to integrate, and we're going to have a differential equation that's going to have an integration of the time rate of change of velocity. But I have to choose the streamline over which I integrate that. And so this can be difficult unless we're dealing with long, thin, straight pipes, where we're thinking about acceleration or the time that's required to get a fluid up to moving at a certain speed. And that comes from the inertia of the fluid. So those are the simplest kinds of problems, and you've probably seen Bernoulli's equation many times now, maybe in a physics course or in an undergraduate fluid mechanics class. And these are just generalizations of that. We spent a lot of time in the first module, however, also thinking about the idea of a control volume surrounded by a control surface. And so we integrated this Navier-Stokes equation, and we ended up with it in a control form that has 2 forms that we called Form A and Form B. And the only difference between them is where the time derivative sits, whether it's inside the integral for the volume or outside the integral for the volume. And the way we interconverted between these was the idea that we called the Reynolds transport theorem, which is essentially a theorem that allows me to convert between a Lagrangian reference frame following a material particle and an Eulerian reference frame, where we typically ask what's the time rate of change inside a control volume or an existing volume. So we had these 2 different forms. We used them, for example, with conservation of mass, which was the continuity equation, as well as the conservation of momentum, which we called the Koshi momentum equation. The Koshi momentum equation, remember, is not closed. It's really three differential equations for Vx, Vy, and Vz. But on the right-hand side, it has the components of the stress, and the stress is a symmetric tensor, so it has 6 unknowns. There's also pressure as an unknown, so clearly this is not a solved set of equations. And we had to specify an equation of state, or what we called a constitutive equation, that really relates the stress in the system, which we call tau, to the velocity gradient and its symmetric part. And we learned that the symmetric part was necessary because that's what told me about stretching, and it's what told me about shearing. And the anti-symmetric part of it just told me about vorticity, or about circular motions, or about rotation. So this was a large part of what we thought about in the second module. We also thought about what happens in the limit of very viscous flows, where the Reynolds number that we learned about from dimensional analysis became very small. And that led to an equation that we called the Stokes equation. The nice thing about the Stokes equation is that it's a linear equation, so it has no nonlinear terms. It had first derivatives of pressure, second derivatives of velocity, and this gave rise to these very interesting ideas that I could reverse the symmetry of this equation. If I change the sign of the pressure, I can change the sign of the velocity, and everything reverses. And we saw G.I. Taylor demonstrate this idea of kinematic reversibility in the material. So that was part of our second module. We also thought about what happened in slightly more complicated flows where we didn't have a truly one-dimensional flow, but we maybe had two very different dimensions, a small dimension and a long dimension. And this led to an idea that we called lubrication problems, or lubrication theory. And so here we thought about the idea that things were fully developed in the small direction because diffusion was very fast in the small direction, but things were still evolving in the long direction, or weakly along the flow domain. And so we had two equations. One was that there was no pressure variation across a streamline, and then the second one was just looked like one-dimensional flow, with the unique thing that the local boundary conditions were different at every different point along the system. And we saw that this can give rise to very large pressures, and this is what we typically think about when we think about lubrication. In the case of a free surface flow, of course, we can't have very large pressures because very large pressures would force the surface upwards. And so instead we combined this, and we had a one-dimensional lubrication problem that connected the volumetric flow rate across the film with an evolution along the film. And here's an example of, for example, where our surface tension boundary condition that we have here can actually be used with the free surface lubrication problem to lead them to a whole class of very interesting kinds of problems. And then finally, we also spent some time in our third module thinking about what happens when we deal not with very viscous fluids, but with almost inviscid flows. And we came back to thinking about potential flow, where the viscosity effects were negligible, and we just had to solve the Euler equation. But we solved the Euler equation in a way that we found it in terms of a velocity potential for an incompressible flow. And that allowed us to solve for it in terms of a nice scalar that we called phi. We also learned about the idea of complex variables, that we could think about phi as a potential and the streamlines as being orthogonal to each other. And then we solved it in terms of a complex potential. And then once we started to think about things in terms of a complex potential, we could think about integrals around objects. And this allowed us to think about the idea of generating lift and drag. And using the Kotter-Joukowski theorem, we found that we could find a closed form expression for the lift in terms of an integrated quantity for the vorticity that we called the circulation. However, we also found that we couldn't calculate any drag in this case. Our drag, which we called d as a drag force per unit width, was actually identically equal to 0, and this was D'Alembert's paradox. And so the final part that we had to think about was, if we couldn't calculate a drag this way, we had to go back and think that in a thin region very close to the boundary, we cannot any longer neglect viscosity, and we have to incorporate viscous effects. And so very final part of the class that we thought about was the idea of thinking about boundary layers. And we developed a set of two-dimensional boundary layer equations, which still satisfied incompressibility. They still had zero pressure gradient across the streamlines. But this last equation in the top here, you can see is still a nonlinear differential equation that contains second derivatives for the velocity. It controls pressure gradients along the flow, which can give rise to either a favorable pressure gradient that keeps the boundary layer attached, or if the flow slows down, then the pressure would be larger ahead of me, and we call that an unfavorable pressure gradient, and that could lead to separation. And so the boundary layer equations are good examples of still nonlinear equations, but they're nonlinear equations that can be solved for us to understand things such as lift plus drag on a surface, as well as the idea of flow separation. So really, this is a summary of all of the equations that we've studied. And really, the main part of this class has been thinking about how to apply these equations to a system of different problems. And so as you go forward, I hope that these equations will be useful. And this page may be a helpful cheat sheet for you. The challenge is to think about how to systematically simplify the problem using dimensional analysis, and then make some approximations that are valid and justifiable, and use the appropriate one of these equations to then be able to analyze a problem of interest. So with that, thank you very much for your attention, and I look forward to maybe meeting you in the future, and I hope that you'll find these equations useful in your career.